of Assistant College of Engineering and the Vice President of the ACM Chennai chapter. She will conduct the proceeding.
Good evening, all of you. So as Vice Chair of ACM India Chennai Professional Chapter, it's my pleasure to welcome all of you for this first talk in the Turing Awardee series of talks which we are planning this evening. This is co-hosted by Institute of Mathematical Sciences. The talk is going to be on the work done by the Turing Awardee of the year 1972, Edsger Dijkstra. So I would like to say a few things here regarding ACM, that is Association of Computing Machinery. ACM is one of the premier forums for computing educators, researchers, as well as the professionals. And ACM has been honoring either a single individual or a group of individuals for their outstanding, lasting contributions in the field of computing in the name of A.M. Turing, Alan Matheson Turing. And he himself has contributed enormously for the notion of algorithms and computability. And this award is considered as the highest honor or the ultimate recognition, and in fact it is considered as a Turing, this is considered as a Nobel Prize for computing. So ACM is planning to celebrate this 50 years of Turing Award, and in that connection we will be playing a short video here. After that I will again come back to the talk of this evening.
Long before many could envision the concept of computers, Alan Matheson Turing saw their tremendous potential to alter our world for the better. Each year, ACM honors outstanding contributions to computing with the presentation of the award that bears his name. In the coming months, ACM will celebrate 50 years of the ACM A.M. Turing Award, as well as many of computing's greatest achievements. First, however, we'd like to show you why ACM chose to celebrate the memory and contributions of Alan Turing.
Alan Matheson Turing was a remarkable visionary who helped shape the diverse fields that would become computer science. In 1936, he launched the modern computer era with his classic paper on computable numbers. In it, he conceived his universal Turing machine, which he then proved could compute anything that was computable. During World War II, while working at Bletchley Park, he co-designed an electromechanical computing device, which his team of codebreakers used to help crack the Enigma codes used by Nazi Germany. In 1950, he developed the criterion now known as the Turing test to determine whether or not a machine could actually think. In 1966, the Association for Computing Machinery instituted the ACM A.M. Turing Award. For half a century, Turing laureates have advanced all fields of computing science, many having emerged since the first presentation of the award.
Turing's role was the visionary. From the rudiments of computing at the time, he was able to extrapolate the immensity of what a, quote, computer, unquote, could do.
There is a new giant around, and that is computation. Computation is the glue that keeps the world together.
40-odd years after we did our original work on the Internet protocols, and the fact of the matter is people are still stuck at looking at screens and keyboards, and many people are 7x24 stuck to them.
An intelligent agent should be equally good for an illiterate person in a village. We should have two kinds of agents: cognition amplifiers, which do things we know how to do, and guardian angels, which do things we don't know how to do.
Often when you make a scientific discovery, you start laughing. And the reason is that the universe didn't change just because you saw something. It was already around us, and like a joke, you just couldn't see it.
To realize that these early ideas, data abstraction and specifications and programming languages and so forth, to understand that they had moved so into the mainstream that everybody knew them, and they were the basis of how you wrote programs. I mean, that was just a remarkable thing to understand.
But now, what I'm trying to do is distill off what I think is going to be of lasting interest. What parts of the things that people are doing today are people going to be interested in 50 years from now?
Today, we have all this tremendous amount of data out there, tremendous amount of connectivity, and it's a really pressing question. Now what?
So there are all kinds of concerns that people have about safety, about reliability of these devices, about their security, and whether or not they preserve privacy.
Everything we do is already known and knowable. I don't think we have any privacy at all.
This space of computing is exploding. It touches so much of everything we do in all the sciences. Now every science is beholden to our ability to compute.
I'm Craig Partridge.
And I'm Fahad Dogar, and we are delighted to serve as co-chairs for an outstanding ACM event in 2017.
Next June, in memory of Alan Turing, ACM will celebrate 50 years of computing's greatest achievements in an exciting conference in San Francisco.
We will feature many of the recipients of the Turing Award, as well as other leading researchers in computer science.
We'll be exploring the evolution of computer science and where it is headed in a series of lively, moderated discussions in which the experts take questions from other experts as well as those attending.
So please, plan now to join us either in person in San Francisco or on the web as we stream these sessions live.
50 years of celebrating computing's greatest achievements promises to be a truly unique experience.
We look forward to welcoming you in San Francisco.
So now it's my pleasure and privilege to introduce the evening speaker, Dr. Madhavan Mukund. He has been with Chennai Mathematical Institute for more than 25 years now, and he is the current president of ACM India. He is also the president of Indian Association of Research in Computer Science, and as part of that, he has been coaching the bright young minds of school children in participating towards the International Olympiad in Informatics. He has also served as executive director of this IOI during 2011 to 14. And he has been contributing lectures to the National Program in Technology Enhanced Learning, NPTEL, in the area of algorithms, Python, and also in functional programming. And his lectures, the hallmark of his lectures are the exceptional clarity and the remarkably practical examples which he gives. And he's really a teacher par excellence. Ladies and gentlemen, please welcome Professor Madhavan Mukund. Thank you. Thank you.
Okay, sorry for the delay. Thanks, Chitra, for the extremely generous introduction. So, I suggested that we should start with a well-known person, and then I was asked to give the talk. So this is my reason for talking here on Dijkstra. So I think Dijkstra is one of the, studies, Dijkstra was Dutch. Was born in Rotterdam, but basically grew up in Amsterdam, I think, and he did his PhD in Amsterdam. A lot of the early people who do a PhD related to computer science, some kind of programming, I forget exactly what he did. But then after that, he moved to Algol, where he spent a large part of his what we would call academic productive life. And then in '84, he moved to UT Austin, where he spent about 15 years. And then he retired and moved back to Holland, where he passed away 3 years later. So these are just some background facts. So I would like to read out. So every training award comes with a citation explaining what they're doing. Right? So this training award says for fundamental contributions to programming as a high intellectual challenge, for eloquent insistence and practical demonstration that programs should be composed correctly, not just debugged incorrectness, for illuminating perception of problems at the foundations of program design. Okay, so you get the idea that you have something to do with programming. But this is, I think, a very narrow view of what he did, as I hope I will try to explain to you, although it was a very important aspect of what he did. So, if you wanted to just list out his contributions in terms of areas and bullet points, okay, what every undergraduate knows, and more than what the MPhil knows, is that he had his shortest path within graphs. Okay. Many people have an idea that there is something to do with programming language design. Certainly, one of the things he's most remembered for is this insistence on writing correct programs. And in a way, he can be seen as one of the pioneers in what we now call software engineering. He also designed one of the early modern operating systems, which I will not talk about at all, but that's a very important contribution to this. And if you ask me, the thing that he is probably most long lived for in terms of his contribution to the computing community is actually his work in distributed computing, which does not even get mentioned in this citation. Right? So he did enough. So what I think is the most significant work is not even mentioned in this citation. But of course, some of that citation came early, but got it in 72. Remember, the first paper was given in 66, so it was actually the 6th or 7th. So, perspective, of course, comes later. At that time, what was most prominent in his work was his work in programming, correctness, programming languages, and so on. So, I tried to run through this in a kind of historical, but not necessarily chronological way, so I'll go topic-wise. And just try to highlight something that I found interesting about his work and his style and so on. The other thing about Dijkstra is very interesting. He was a very colorful personality. So, there are a lot of stories about him by he's a very quotable person. He said a lot of quotable things, some deeply, I would say, hurtful. And so, it's always entertaining to talk about somebody like that. So, let's start with the thing that is probably most familiar to students of computer science, which is the shortest path algorithm. So, this appeared in 1959. That's really roughly very in this PhD, so it's probably his first published work. And I said about two problems in connection with graphs. Okay? Connection is spread with this previous old English slide. And the problem of shortest path was basically given, he wanted to find, given a graph, which I didn't know very well, find the shortest path between 2 points. And the point is a graph, you can think of it as a railway network or an airline network, as you see in the brochure, you find a sea pocket in front of you. So it's just a bunch of points connected by lines, and it might say from here to here it is so many kilometers, and from here to here so many kilometers. And now, given this, you want to compose these lines and find the shortest path from one place to another. And one of the things he realized is that in order to do that, you want to find the shortest path from where you are starting to everywhere, because you have to go through various places to get there. So the process of finding the shortest path to where you want to go involves, in turn, finding the shortest paths of various places you have to go in between. Right? So this became what is now known as the single source shortest path problem, where you compute the shortest path to everything. Now, I'm not going to tell you how it did it, but the point is that that is only one problem, and this is a node on 2 problems. Okay. So this is a note on 2 problems, and this is the paper. Okay, so you can't read it, but at least you can appreciate that it's about 2 plus epsilon pages long, right? In fact, if you can read this part, somewhere here, it starts with some remarks. So actually the paper ends here. Okay? And 1 page of this is the shortest path problem, which our undergraduates are not able to understand even today. Right? So it's amazing, if you ask me. So this is one of the hallmarks of Dijkstra's style, which is that he could write very complete and clear, concise technical stuff in a way that's one could understand without wasting a lot of space. So the paper is over 2 pages long, and the point is it addresses 2 problems. So actually the first page is not about shortest path. The first page is about spanning trees. So in actually Dijkstra rediscovers what is now called the Prim's algorithm. And if you actually study Dijkstra's algorithm, normally you study it before Prim's algorithm and you say, oh, Prim's algorithm looks like Dijkstra's algorithm. But actually for Dijkstra it was the other way around. He first presents Prim's algorithm and then he extrapolates that to find shortest paths. Okay, now it so turns out that Prim had independently done this 20 years ago, and as we will find out, it's not surprising that Dijkstra did not know about it. But the point is that he did 2 things. So the second page is the shortest page. Right? So there are 2 plus epsilon pages. The first page is Prim's algorithm, the second page is Dijkstra's shortest path algorithm, and the third page is references. So this is typical of the style of Dijkstra, and of course, I think other than this, there is nothing memorable that he has done in the classical framework of algorithms and complexity. So this is kind of an isolated point sort of in his work, but it's a very important point which many people, especially many undergraduates, come across early in their study. So a more long-lasting and visible effort and contribution of Dijkstra was programming languages. So he was deeply involved in the design of this language called Algol, which went through various versions, and the versions are named after the year in which they were kind of laid down. So Algol 60 was the first, what you would call in modern parlance, the first stable version of Algol probably. So the importance of Algol was before Algol you had languages, so Fortran existed, but there was really not much by way of high-level programming languages, and there was not much clarity on what a programming language should look like. Right? So if you look at Algol 60, you see for the first time a programming language that looks like a modern programming language. So if you look at any modern programming language, by which I mean C, C++, Java, any of these kind of things, the structure of these programming languages derives directly from the ideas which went into Algol 60. Right? So you have blocks like begin, end, you know, things are kind of in, you have these ifs and whiles which have these blocks, and then you have functions inside functions, and you have some notion of where a function is visible in terms of the text, you have lexical scope. It also introduced other ideas which did not exist previously, that you have to describe the language in a formal way. So this idea of a grammar to describe the language. So the famous Bacchus-Naur form, which is now very well realized as a standard way of describing programming languages, actually was invented during the formulation of Algol 60. So as I said, Dijkstra was part of a committee that worked on this. Probably, this is something again I did not know until I prepared this talk. One of the things that Dijkstra is known for is to have actually sneaked in the idea of recursion into Algol. So see, it was designed by a committee, and programming was kind of new, and recursion was a strange and scary idea. So Lisp existed, but Lisp was seen as a strange and unnatural programming language for geeks, and real programmers could not make any sense out of it. And so people were deeply worried about introducing recursion into a traditional language. But on the other hand, Dijkstra was convinced that recursion should be there, and there was a kind of a private tussle between the people who were writing the report, and then there was some clause. So it was like this language was described like a whatever, like a legal document, 5.4.4 and 6.2.3 and all that. So I think 5.4.4 in particular talked about what happens when the name of a program appears inside the name of a program, and nothing was said. So Dijkstra said, oh, you know, this thing is missing, why don't you add the sentence that if you see the name of a program inside another program, it means you start that program again. And it appears the other people did not realize that this meant recursion, right? So they signed off on this, and then after they were furious to find out that they had actually introduced recursion into Algol. Now, notwithstanding his victory on this front, I think he did not have his way on other fronts, so actually he refused to sign this, he refused to be an author of this. So the actual Algol 60 committee does not list Dijkstra as a member. He did not sign off on this because he differed with some majority opinion. It's not very clear to me exactly what he differed with, but it didn't stop him from writing the first Algol 60 compiler. Okay, so he went back to his department in Amsterdam, and along with this other person, Jaap Zonneveld, he wrote the first Algol 60 compiler. Right? So he was very much involved in this modernization of programming languages. Now, as I said, Algol was an evolution which went from one stage to another. So now after Algol 60, people started looking at, improving in some sense Algol. And the next phase was something which came out eventually in 1968, which was called Algol 68. So by then there was this body called IFIP, which had these working groups dealing with different aspects of computing. And working group 2.1 was supposed to be doing programming languages, and they were supposed to be redefining Algol. So Niklaus Wirth actually came up with some ideas for Algol, and then there was a competing design from some other person whose name I've forgotten. And unfortunately for Algol, Niklaus Wirth was the one who lost the argument. So Niklaus Wirth's ideas eventually became Pascal, and which was immensely widespread, say in the 1980s, as a programming language, and still persists in some places as a language for teaching programming. I learned Pascal as my first programming language, and I think it's still a good language to learn programming with. So as a result, what happened was that Algol 68, so Algol 60, despite his differences of opinion, I think Dijkstra secretly liked the language. Algol 68 he could not stomach. So as was his style, right, he doesn't keep quiet, as we'll find out. So he wrote a sort of an open letter to the committee and published it. He wrote a letter and published it so that it was no longer a letter. Right? So this is what the letter looked like. Right? So this thing is, I just wanted to note, so this is supposed to be a formal letter to the committee which designs a language. Okay, and this is how he starts. He says, there are writings which are lovable although ungrammatical, and there are other writings which are extremely grammatical but are disgusting. This is something I cannot explain to superficial persons. Okay, this is a letter written to colleagues like Hoare and Niklaus Wirth and people like that. Okay, so this is what he calls the reader's reaction. And then what he calls the writer's reaction. So if you have heard this, there's a wonderful song by Tom Lehrer, which says, my tragic tale I won't prolong, sing rickety tickety tin. My tragic tale I won't prolong, and if you did not enjoy my song, you've yourselves to blame, for if it's too long, you should never have let me begin. Right? So this is his preamble to this letter to this committee complaining about Algol 68. And here are some of the comments he says. He says, the size and complexity of the defining apparatus you need terrify me. Okay. This is an innocuous comment. Then he goes on to say, being well acquainted is a kind of left-handed compliment. Being well acquainted with your ingenuity, I can only blame the language. Right? The fact that you chose this language and not some other language, you couldn't do anything better, knowing how smart you guys are. Okay? Then he goes back to, remember this IFIC working group 2.1 is created for programming, right? So he said WG 2.1 should return to its proper subject matter, which is programming languages. Meaning to say that this last 8 years or whatever you've done is not programming languages. Okay, so this is his take on Algol 68. Algol 68 was actually a very ugly and unusable language with too many features, and nobody could figure it out, and it never caught on. Okay, so it was never actually made into a mainstream language. Nobody actually wrote programs in Algol 68. But this was kind of typical of the way that Dijkstra's interacted with the community, even his peers around him. Okay, this is very much his style. So, in a sense, what this did indirectly, okay, so some have debated whether this is true or not, but in a sense, Algol 68 convinced Dijkstra that the problem is not in programming languages, but in programming. Right? So this is a quote. So there was a committee which talked about this software engineering problem which met after that, and one of the members of the committee summarized Dijkstra's point like this. So this is just a quote. He says the true problem is now the reliable creation of programs to perform specified tasks rather than their expression in some language. Right? So the point is no longer what the programming language is. The point is what are you trying to do. Okay? So he goes on to say, I doubt if any programming language, as the term was and still is understood, would have satisfied him. Okay? But the point is that this is kind of in a way, a transition point in Dijkstra's thinking, where he's not worried anymore about writing the perfect programming language, but worried about how you actually write software. So corresponding to the citation of the Turing Award, there is a Turing Award lecture. And this is the title of Dijkstra's lecture, which he gave on receiving the Turing Award, called The Humble Programmer. So he talks about his background and how he got into programming. But somewhere down the line, he starts talking about this whole issue about software engineering. So this is really, in some sense, his first public pronouncements on these topics come around this time. So he says that as long as there were no machines, programming was not a problem. When we had a few weak computers, programming became a mild problem. And so now we have gigantic computers and programming has become an equally gigantic problem. So his contention was that as the power of the machine to execute and the expectation grows, you write more and more complex things and you understand less and less what you've written and you are unable to fathom whether your program is doing what you think it's doing. Right? So he also coined, now this is another thing, there are many things which I didn't know that Dijkstra said first, but he's probably the first person who wrote this phrase. Right? So is it a wonder that we find ourselves in a software crisis? So this is part of his Turing Award acceptance address. Right? So he's basically moving from programming language design to program design, as it were, and indirectly towards what we would now call software engineering. So this is around the time that he started strongly advocating this notion of structured programming. So the idea with structured programming is that you have these blocks like if, then, else, while and all that, and then you can reason about your program in terms of these blocks and build up your understanding of the program by building your program systematically out of these blocks. So in this context, I should mention something which he did. So this is early 70s we are talking about. But there's a very famous letter which he wrote in 1968, which actually apparently the title of this letter is not his. The title of this letter that he wrote was a little bit more innocuous. I forget, a comment on the go-to statement or something like that. This is Nicholas Wirth who made this title like this because he wanted to draw attention to it. So it came as a letter to the editor in CACM, the communications of ACM. And basically the crux of his argument was that the go-to statement is an invitation to make a mess of one's program. Right? So he strongly advocated that go-to should be banned from programming languages. And in fact, I think that, if I'm not mistaken, the first modern programming language without a go-to is Java. So this was part of this structured programming thing. So the idea was that you should have your control of the flow of your program should be in kind of manageable units, and you should be able to reason about these units in a constructive way by building up your reasoning. So more specifically, around this time, he was focusing, as I said, on deriving correct programs. So this is another one of his quotable quotes. So remember that, if you remember the citation, it said that programs should be built correctly and not by careful debugging. That was one of the statements in the citation. Right? So this was one of his famous statements which he made in many different forms, but this is apparently the shortest Kolmogorov complexity version of this quote. It says, testing shows the presence, not the absence of bugs. So his point is that if you debug, okay, what will you find? If you find a bug, then your debugging has told you something. But if you don't find any bugs thanks to, if you don't find any mistakes thanks to your testing, it doesn't give you any assurance that you've written the right program. Because you're only testing against what your expectation was, and that's inadequate. So you must actually build your program correctly, systematically. So he formulated this way of thinking about it. So he said that you execute, now this remember in a structured setting. So in a structured setting, your whole program can be thought of as one big statement, which is broken up into these blocks, which are independently blocks and blocks. So it's a kind of a like whatever, this babushka doll kind of thing, right? So ultimately you're only reasoning about one statement and what happens after that, and what you're interested in is what happens after, right? You're writing a program to achieve an objective, so you write down that objective, call it R, okay? So R is the desired property after the statement S executes. So now your question is, if I want R to happen after my statement, what should be true of my all the values that I'm computing before I start R, the statement, right? And this he called the weakest precondition, right? So this is the set of initial conditions from which I'm guaranteed that if I run my program, I'm going to get R. And this is the basis of his notion of deriving correct programs. Now it's an extremely tedious and manual process, and it doesn't scale. That's a different issue. But he had the idea that there is something which is beyond just writing code and then going and applying tests and seeing if all the tests pass. That you have to think seriously about what your objective is, and try to see if you are achieving that objective systematically by analyzing what your statement is doing. So in his in the same paper where he talks about this, he introduced this idea. So what is R? R is what you can call a predicate, right? It's a property, it's a logical formula about your variables. X is less than Y, AI is less than AJ for every, whatever. So some property about your variables. And this property, after the program executes, the property changes. So the predicate changes, right? So in his view, a program is something that transforms a predicate on your things into another predicate. Right? So a program as a predicate transformer. So these are all, I'm not going to go into any more details, but these are all influential ideas which I think many people worked on. As I said, some of these ideas don't scale, so in a modern setting you don't, but people are going back to this in a different way. Okay, they're using these ideas in a different way to do automated verification, to try and guess these assertions and so on. So along with this, although I said he had kind of abandoned programming languages as such, he still had an idea that programming notation is not ideal. And in part this is due to his work in distributed computing, which I haven't yet talked about. But he said that this if then else he felt was too asymmetric. So basically he said what we should do is we should actually think of what he called a guarded command. So we have a bunch of things. So if then else is saying if a condition holds, then do one part, otherwise do another part. So he said, why should we have this mutual exclusion, this or that? Okay. So he said, okay, you have a bunch of conditions and you have a bunch of things, and one of them or more of them could be true. So here is an example. So this thing is trying to figure out the maximum of two values x and y. Right. So there are two statements, the first statement and second, and there is this kind of thing which sometimes can be drawn as a rectangle, which says that I have a choice between that and that, but the choice is dictated by this condition. So if x is greater than or equal to y, then m will be assigned the value x. If y is less than or greater than or equal to x, m will be assigned the value y. Right? Now if you write an if then else, then depending on how you phrase that, greater than, equal to, or greater than, right, then you will either, if they're equal, one of them will be copied, x will be copied or y will be copied. So it depends crucially on whether you write that initial thing as greater than or greater than equal to. As to what happens when the two are equal, which one, it may not matter to you so much, but it depends on what assignment means. Okay? So his point here is that this is actually, you don't know. Right? If x is equal to y, both of these are true. Y is greater than or equal to x, x is greater than or equal to y. So you are not sure whether m gets assigned x or m gets assigned y, but as far as you are concerned, it doesn't matter. M is still the maximum. Right? So his point was that this kind of notation simplifies arguing about these things, and it removes some kind of sequential analysis which you have to do in this if then else. Because if then else kind of makes a priority out of this condition and then this condition and this condition. So if you have a choice of conditions, he felt this. Now just to illustrate this, he came up with this example. So this example is trying to arrange 4 values in non-decreasing order. Right? So what he says is, okay, so you have these initial 4 values which are these capital Qs, right? And then you assign them to your values small q's, and you finally want that small q1 is less than or equal to small q2 is less than or equal to small q3 is less than or equal to small q4. So initially they could be any arbitrary values. So what do? You just keep checking. Okay, if the thing is wrong here, if q1 is bigger than q2, you exchange them. Now if you have anybody here has studied Python, okay, you can see where Python got this simultaneous assignment operation. right? So it says assign Q1 to Q2 and simultaneously, so this exchange the values of Q1 and Q2. Same way, if Q2 and Q3 are not ordered the right way, exchange the values of Q2 and Q3. Same with Q3 and Q4. How long do you do it? Well, you do it indefinitely. So this is that is an if which you do once. This is a kind of infinite loop which you do until nothing can happen anymore. So basically, on their own, spontaneously, these values are rearranging themselves so that the first value is less than the second value is less than the third value is less than the fourth value. Okay, so this is a style which he introduced. So this is a notation called guarded commands which Dijkstra introduced, and it's actually quite popular in describing many kinds of algorithms. It's also used in some verification tools, like there's a very powerful tool called Spin, which is used for verifying concurrent protocols. So this is a part of it, but it's actually related to his correctness thing, and it's not, he doesn't expect you to write code like this. I mean, it's not he doesn't have a compiler for guarded commands, but it's more like a specification style. Right, so moving along briskly. So coming to distributed computing, or more precisely, I would say concurrent programming. So Dijkstra was one of the first people to envision this idea. So, I mean, you can imagine that this is the early 60s, and he is already thinking about the fact that computers are not working in isolation. Right? Computers are working in a way where they have to interact with each other. So in 68, he finally wrote a very long and somewhat influential monograph, I guess is the best word for it, called Cooperating Sequential Processes. And it starts off by introducing Algol 60 notation as a good way of writing programs. So basically it's aimed at the person, what you might call an intelligent layman who doesn't know anything about programming. So it starts off, the first chapter is about describing how to write down an algorithm in Algol 60. And then rapidly he moves on to this question of what happens when these things are running simultaneously, and periodically they need to interact with each other. So they're not running in a kind of synchronized way where they coordinate, so there's no timing assumption or whatever, but they need to periodically interact with each other. So the first problem he identified, and one which is still the most canonical problem in this, is the one of mutual exclusion. Right? So if you have two machines on a network, and two people are trying to print, you would like to ensure that they don't print on the same printer at the same time, otherwise you'll get some jumbled printout. Right? And this is a typical problem which happens any number of times with any number of different things. So you might say the same thing about accessing, say, a reservation system. You would not like two queries or two bookings to be made simultaneously on a reservation system and grab both of them claiming to grab the last seat available. Right? So this is a very quintessential problem of concurrent programming, and it was not entirely clear to me until I started reading about this, that actually Dijkstra in some sense was the first person to identify it and name it also. I mean, he was the first person who identified mutual exclusion as the heart of concurrent programming. Along the way, he also talks about, for the first time in the literature, problem of deadlock, where two of these agents or computing agents are trying to synchronize with each other, and each is waiting for something that the other one is supposed to do, and they can't solve it. I mean, so like this entrance to Ramanujan city, that road, right? So everybody is trying to block each other, and nobody is willing to go back, and then everybody is stuck. So he called it the deadly embrace, but soon it became called deadlock. Perhaps a little bit more, again, farsightedly, he also said that this is a problem that cannot be solved on your own. Right? You as a programmer, you need some way of enforcing synchronization. So this is some support which has to be given outside your normal assignment statement and while statement and all that. You need some extra thing, because this is not something that you can just wish away. So he invented this thing which we now call a semaphore, which is a way of coordinating between two of these processes and allowing them to ensure that both of them will not get into this critical section, as they call it, this mutual exclusion. Both of them will not try to do it. And he also, for instance, invented this very famous example which is used as a benchmark for many various solutions and or notations for concurrent programming, called the dining philosopher's problem. So the dining philosopher's problem imagines that you have a group of, say, 5 philosophers sitting around a round table, and they have a fork between each of them. So there are 5 forks situated between the 5 philosophers, but unfortunately each philosopher needs both forks, the one on his left and the one on his right, to eat. But the one on your right is also shared with your philosopher on your right, so there is an issue that if that guy grabs the fork, so if everybody grabs the left fork first, then you have deadlock, because nobody is going to get the right fork, right? Because there are only 5 forks and they have to eat. So the question is, how do you design a protocol where everybody will get a chance and without, literally starving people out and so on. So all of these things actually were so this dining philosophers was actually a homework exercise. He set it as an exercise for his students. And again, I think his name was slightly less poetic, and I think Tony Hoare was the one who called it dining philosophers. His thing was dining something else's. But the point is that all these ideas actually stem from, originally from Dijkstra, which is something surprising to me. So he did more. He also invented a class of algorithms called self-stabilizing. So this is important when you have faults in your system. So supposing you have some kind of a protocol running, and then one of the key elements of your system goes down, then somehow you have to re-establish that protocol. And so he came up with algorithms which will do that. And this has again been an enormously influential area of work in distributed algorithms. He also described the first formally correct concurrent garbage collecting algorithm. So garbage collection is something that happens in languages like Java and Python and all, where you don't explicitly dispose of memory which you have dynamically allocated. And the system is supposed to periodically check whether some values are no longer being referred to in your program and return them to the free space. Now, if it runs as a sequential thing, that it stops your program and restores the free space, obviously there is a performance issue. So the ideal thing is that this garbage collection should run while your program is running. But then the problem is that your program is at the same time consuming and returning things to memory while this garbage is being collected. So how do you ensure that there is no inconsistency between what the garbage collector thinks is unused memory and what your program thinks is used memory? Right? So this was also one of the contributions of Dijkstra. So one of my justifications for claiming that this is his most well-known contribution is that this is one of the few things which is actually named after him. So there is an Edsger Dijkstra Prize in Distributed Computing, which is for the most influential paper in the area, and it's awarded alternately at these 2 principal conferences, Principles of Distributed Computing, PODC, and DISC, which is, it's got some funny, it's one of these European names which is not to be read in the order in which it's given. So they alternately give it. So one is the American conference, one is, so ACM, PODC is an ACM conference, and DISC is a European Association of Theoretical Computer Science conference. Right? So this is the prize which is in his name, and it is in the area of distributed computing, right? Which is not even mentioned in his Turing Award. So one of the things that Dijkstra is well known for is, as I said, the clarity of his writing. As I showed you, even as early as his very first work on shortest paths, he writes very crisp and very concise but clear definitions, proofs, theorems. Everything is written in a very precise way. And there are limitations also, so he would refuse to use complicated notation, but which also limits what you can do. For some strange reason, apparently he also had an aversion to using pictures. So he felt that pictures are not, if you need a picture, then something's wrong. Right? So he would never draw a picture. And there are no pictures in his papers at all, actually. Apparently he had a rather cavalier approach to references. So this goes back to the point that he rediscovered Prim's algorithm. So part of the reason he rediscovered Prim's algorithm is because he didn't bother to find out if somebody else had worked on this problem before or not. And so there is an instance of this which is self-documented. So he wrote this book called Discipline of Programming. And in the introduction he says, for the absence of a bibliography, I offer neither explanation nor apology. Right? So he writes a whole book with no references. And this is typical of his style. So in fact, he wrote another book. So this book, I think, survived. He wrote another book, whose name I've forgotten, but which got a scathing review because it was basically claiming to prove things like, you know, equality is associative and things like that with respect to propositional logic. And the reviewer who reviewed it said that, you know, clearly this person has got to go and read more about what logicians have done for 100 years before claiming to have invented propositional logic. So not everybody subscribed to this style that all was discovered by himself, but he clearly discovered everything himself in his opinion. So this was about his writing style. Now, he was also, as you have noted in that letter to the Algol committee, not exactly polite or, you know, diplomatic about his choice of words. Most often it was interesting that most often it was actually put down in writing. Okay, it's hard to withdraw something which you have written to somebody, but sometimes it was also apparently, so by all accounts he was not openly rude in person, but there is this incident which was quoted in his obituary by Christoph Abt. So apparently there was a lecture by some famous MIT professor who was unnamed when he was in Austin, and at some point she said, I'm losing my voice, and it seems from the back he said, thank God. And then as a afterthought, apparently the chairman of the department had to write an abject apology to this visiting prof on behalf of Dijkstra. So apparently this is not typical, but this is, I mean, he didn't do this often, but he has done things like this. Right? So the flip side of this, so if you watch that movie, one of the Turing awardees in that movie was a person called Alan Kay. So this is what Alan Kay had to say when he gave a keynote speech at a conference. He said, you probably know that arrogance in computer science is measured in nano Dijkstras. Okay? So this is when he was still alive, by the way. He died only in 2002. Right? So he just got back what he was giving. So certainly he was a colorful personality. And I said he's extremely quotable. There are a lot of quotes which are about things where he says nasty things about objects, like he complains about programming languages like COBOL and Fortran and all that. But I thought I should entertain you by abusing some of you here in the audience. So the first quote is for my colleagues from physics. So it says, in the good old days, physicists repeated each other's experiments just to be sure. Today they stick to Fortran so they can share each other's programs, bugs included. Okay, so this is just typical of the kind of comment he would make. Now, not to spare computer scientists. So if you remember, there was all this talk about Alan Turing and the Turing test and can computers think, right? This is what Dijkstra has to say. The question of whether machines can think is about as relevant as the question of whether submarines can swim. So you can take whatever you want of this, but there is a whole web page of quotes, and some of them are mildly amusing and some of them are dated and so on. But it's interesting that, you know, he could hold forth on everything and you know, never let an opportunity pass where he could give an opinion on something that he thought was worthy of giving an opinion on. So I would claim that Dijkstra was the world's first blogger. So he wrote this sequence of manuscripts, which are later numbered as EWD for his initials, 001, 802, and so on. So everything that he wrote, including his papers, okay, are available in some form in this manuscript. So some of these are technical notes, so some of them are preprints, okay? Some of them are just trip reports. I went to this conference, I liked this talk, I didn't like that talk, the weather was awful, the road was fine, and all that. Some of them are observations. Okay, this style is bad, this style. Some of them are commentaries. Okay. So the earlier ones of these were typewritten on this old typewriter, okay, and the later ones were handwritten. So this is what a typical, so this is the one about guarded command. So this is an so you can see the EWD 418 on the top. Okay, so this is typed by Dijkstra. Okay, this is his thing, and this is a handwritten thing, which came a little later. You can see the numbering. So it's 898. Okay, they are not consecutive. There are a lot of things that he threw away. So it's not that he has written 898 of them. But every time he started a new one, he would give a new number, and then some of them he never finished, or many of them he never finished. But there are a good number of them. Okay. So the question is, do you recognize this handwriting? Right. So this has actually been converted into a font. Right. So Luca Cardelli, who is now a researcher at Microsoft Research in Cambridge, UK, and who has designed a number of interesting logos and things for computer science, actually created this font. And it seems when he first created it and he sent a document in this font to Dijkstra, Dijkstra did not realize that it was actually not handwritten. So he was very thrilled with this fact. Okay, so you can download it and you can use it in your own presentation if you want. Right? So there is a Dijkstra font. So I'll close with one of my favorite EWDs. Okay, so there is one EWD, I forget the number, you can look it up, which is called a parable. Right? So this is a story. So it says, a long time ago there was a railway company, and they had these coaches where passengers could sit, which had toilets at one end. So the board of directors of this railway company decided to cut costs and remove toilets from 50% or create new coaches without toilets, so that only 50% of the coaches had toilets. So what was the outcome of this? The problem was that this board decision was not communicated to the people who actually assembled the trains and put them out to run. So the toilets were distributed in a random way across trains. So some trains had toilets in every coach and some trains had no toilets and so on. So the complete chaos. Right? So then they said, okay, you can't do this. You have to put toilet coaches on every train, right? So you mark the coaches outside, saying whether it has a toilet or not, and then you make sure that 50% of the coaches in every train have toilets, so all trains are covered with toilets. Okay, so it's kind of makes life more complicated because you have to now make sure that you count and all that. So when you are doing this, the people who are doing this are not terribly amused. But of course, this doesn't completely solve the problem because it doesn't guarantee that the toilets are distributed across the train. All the toilets are in the front half, and the back half there are no toilets. Okay, so the passengers are not amused by this, so more complaints come back to these famous directors. So then they tell these guys, no, not half, alternate. Right? One toilet, one no toilet, one toilet, one more toilet. But the problem is still not resolved. Okay, and that's because, remember, the toilet is only at one end. Right? So you could have a situation where this toilet is at this end, that toilet is at that end, and the alternate coach in between. So there is a section which is almost 3 coaches long between toilets, which is not the intention. Right? So here he says the parents of small children were not amused. So one of the problems is you don't know which way to go. Right? So he said, okay, make sure that the toilets are all pointing the same direction, so you don't have this three gap. It's only 2 gap. But even if you have only a 2 gap, if you're sitting inside, right? So you're sitting in a coach which doesn't have a toilet. Now, is your nearest toilet to your right or to your left? It might be that you have to walk 1.5 coaches to reach a toilet if you go the wrong way. Right? So where is the toilet? So then you say, okay, inside we'll put an arrow saying toilet is that way, or nearest toilet is this way. Okay. But now what has happened is that even the coaches, so first of all the coaches with the toilet have to all be put facing in the same direction. Now all the coaches without toilet also have to be put carefully, because the arrow is inside also, to facing the correct direction when you put them together. So it's getting more and more complicated. Right? And then somebody has some light bulb. Okay. So they say, you take a toilet coach, you take a non-toilet coach and put a toilet in the middle. Now you can say on the other side that this is the nearest toilet. It's fine. But it doesn't matter if you rotate it around, it's still the nearest toilet. Right? So now each pair is now identical. And it doesn't matter whether the pair is facing that way or this way. So you assemble your train in pairs. And each pair is a pair of coaches with a toilet near the middle. It's either on this side or that side. It's approximately in the middle. Right? So it's not a perfect solution. You might still have to go a little bit longer than you wanted to. But as he said, life goes on again. So this is the parable. Now comes the conclusion. Okay? So according to Dijkstra, okay, so he said the anonymous hero who found the solution deserves to be called the world's first competent programmer. And he goes on to say that programmers are delighted with this story. Then he says, managers get more and more annoyed as the story progresses. Okay, but this is not the end of Dijkstra's nastiness. So he says, mathematicians don't see the point. Right, so this is my favorite EWD, but there are a lot of gems like this. I encourage you to go and read them. Yeah? Thank you. So I should also mention that unlike Dijkstra, I have some references. So the first reference is actually a nice one. This is about 7 pages long. You can get it from, you don't have to go to the journal. Christoph Abt has a copy on his webpage. So it's a nice obituary cum biography of Dijkstra. And then there is a whole wiki quote page with Dijkstra quotes. And at Texas Austin, they actually maintain an archive of all the EWDs. So the EWDs are available both in the original scanned form as a PDF, but they're also been transcribed into HTML, so you can just read them and, on the screen. So you can go and, I think almost everything that Dijkstra did is there in EWD. Thank you.
Thank you, Professor Madhavan. And any questions from the audience?
There is a Dijkstra quote in the corridor right outside this auditorium. People can hunt for it.
Any other questions? No questions. So we would like to thank Professor Madhavan, and as a token of our appreciation, Professor Saktivel will give a memento to Professor Madhavan. Yeah, the tea and snacks are outside, so you can go and enjoy. Thank you.